Welcome to Chapter 4. We'll be talking about inner product spaces and projections. All right, so let's start with inner product spaces. Our goal is to define a product on general vector spaces akin to the dot product in Rn. So if I take two vectors, v and w and Rn, we define a dot product of v and w, and it's quite an easy computation. You just take the product of the corresponding entries and you add them all. All right, so part of the reason we used it is that there are tons of application. Here are a few things that we learned in Linear 1. If you take the dot product of v with v, you get the length of v squared. A dot product is equal to the length of v, length of w, and cosine theta, where theta is the angle between v and w. In particular, this means that if we want to test whether two vectors are perpendicular, let's remember this symbol for perpendicular, then all we have to do is to take a dot product and check whether that gives us 0 or not. And one other thing we did with the dot product is we actually computed angles, right? Solving for theta in this equation gave us that theta was arc cos. The angle between v and w is the arc cosine of the dot product divided by the two lengths. One thing that will be particularly interesting for us this chapter is to do projections. So if you remember what we did in Linear 1, we can split any vector v into a vector projection that's parallel to D and an orthogonal vector which is perpendicular to D. So if I look at this picture, you drop the perpendicular, the projection would be the part that's parallel, and the second vector here that links a projection back to V, that's called the orthogonal. Right? And if you remember the formula, the projection was V dot D over D dot D times the vector D. And the orthogonal is just V minus that. So V minus V dot D over D dot D, D. All right, so in this section, we'll define a similar product on general vector spaces. We'll talk about angles and lengths. And in section 4.2, we'll construct projections on vector spaces. All right, so the same thing we just did, we want to have it for general vector spaces, and it's not going to be along a vector. We could do it on any subspaces. So we could project down to a plane, onto a line, and all of this.